You ever look at these things and think, like, what the heck is that? Like, what is a sunspot? Because isn't it kind of terrifying? Something is blocking out the sun. There is a black spot on the sun. Can it grow? Can it move? How big? What is the maximum? What is the maximum sunspot? Recently there was an eclipse, which got me thinking about this. The moon blocks the sun, right? Lasts like a minute, 2 minutes tops. And it gets cold. It gets dark. Could you have a sunspot so big that you had an eclipse for like a year and a half? I find myself more attracted to the sci-fi that's realistic and realizable and has interesting implications of actual physics things we see. So I wanted to workshop some stuff. But I have not read all the sci-fi or seen all the sci-fi, so I could be missing obvious things. So if I say anything that screams a book you read 5 years ago, please link it below. Okay, so here's a cartoon of the sun. At the core, you have nuclear reaction, where the sun is taking two hydrogens and slamming them together and making a helium, and it releases a bunch of energy. And the sun is like an onion, so outside that nuclear core, you have a radiation zone, where all of that energy is being shoved out via radiation through this plasma. And outside of that, you have the convection zone. So from your thermodynamics, you know that you can transfer heat through radiation, but you can also transfer heat through convection. So you have these little cells where the hot stuff here is rising up because heat rises, and it's heating the photosphere of the sun, and then the cool stuff comes back down and picks up some more energy, and you get convection currents making heat go outwards. Okay, if you look at this diagram, you'll see the sun has all these layers at different temperatures, which is how we can observe a lot of them by looking at different wavelengths. And if you remember from Planck, the temperature of an object is related to its color by the wavelength of the photon that's being emitted from that object. So we can learn a lot about the sun by looking at it in different wavelengths. So what the heck is a sunspot? How do you get a black spot on the sun? What does that mean? Sunspots are normal things to see on our sun. Here's a picture from 2014, and NASA has handily put to scale Jupiter and the Earth with relation to this sunspot. And you can see that these are big honkin' boys. Let's look at a close-up of a sunspot. You have the umbra, which is a dark region that looks black, and then the penumbra, which is a little less dark, and then just a normal sun. And sometimes you get these little filament sunspots called pores, which just evokes, let's not call it that. So a couple things we know about these guys from observations: they always come in pairs. When you look at the magnetic field of these objects, you'll find that one of the pairs has like a north pole and one has a south pole, which means they're connected by some sort of magnetic field. The reason they look black is a kind of optical illusion similar to Mach bands, where when you put two colors close together, the difference in the colors looks more severe. That's by Ernst Mach. You might have heard of him. But really, we can measure the temperature, and we know that they're colder, but they're not cold. So what is a sunspot? Here's another little cartoon of a sunspot. So what you see is a magnetic flux tube leaving the sun and then re-entering the sun. That's how you get the pairs, and that's why they have opposite poles. And you see that this happens right at the convective region, like right on the photosphere, where the convective region is giving energy to the photosphere. So you have these little cells moving heat around. If they come up against a flux tube, they can't get in it. They can't cross that magnetic field. In the region where the magnetic flux tube is, you don't get that heat transfer. That region of the sun starts cooling down. And these guys can last hours to weeks. We see them move across the sun. We associate these sunspots with regions where the magnetic field of the sun is very strong. And they also result in things like coronal mass ejections or like solar flares. You could ask how we can measure the magnetic field of the sun. How can we tell where there's a strong field or a positive field or a negative field? And you do that by looking at the spectra of the sun. So just like using Planck's method to determine temperature from color, you can use spectra to measure magnetic field due to something called Zeeman splitting, where if there's no magnetic field, you have one line, and if there is a magnetic field, it splits into two lines, and the distance that splits tells you the strength of the magnetic field. So we can actually look at a lot of the sun's magnetic fields, beautiful images, or over here. Is there more space over here? So that's what a sunspot is, but it doesn't say why a sunspot, and it actually has to do a lot with the sun's magnetic field and differential rotation. So you have a sun, it has a magnetic field, just like the Earth's magnetic field, a nice little dipole. However, the sun rotates, and the sun is also a big boy. So the equator of the sun is going to rotate faster than the poles of the sun. So that differential rotation causes the magnetic field lines to twist and bend or even snap, and that's how you get things like sunspots and the related mass ejections and all that good solar activity because of the differential rotation of the magnetic fields. And we actually see the solar activity increase and then decrease over a cycle called the solar cycle, and that's because the magnetic field of the sun will reverse poles every 11 years or so. So it will get all twisty, and then the field will reverse and kind of repair itself, and then as the sun starts rotating, it happens again. This process appears pretty regular, and we have been tracking it in one way or another since the 1600s. Here's some drawings by Galileo of sunspots as they move across the surface of the sun. One of the ways we track is by looking at the sunspots and measuring what fraction of the sun is covered by sunspots at any given time, and it's a lovely plot that looks like this going back to the 1800s. And we number the solar cycles just in counting numbers, so right now we're in solar cycle number 25. So you can see differences in these solar cycles. Like sometimes the peak of solar activity is much higher than other times. Sometimes there's a tail on how long it takes the sun to go from maximum to minimum. It is pretty regular, which is good news for us, which I will get into a little bit later. You can also make what's called a butterfly diagram. You can track the position of the sunspot on the sun and the number of sunspot in the sun, and you get this nice diagram as it moves forward in time. Again, you can see differences from cycle to cycle, but it's a nice regular pattern. We have a model for how the sun works and why we get this nice 11-year cycle and why we have periods of maximum activity and minimum activity. This is called the Babcock model, or the Babcock-Leighton dynamo model. Babcock, there are two Babcocks in astronomy. It's the sun. And Leighton is Bob Leighton. He's a famous physicist professor from Caltech in like the 60s and 70s and 80s. What they do is they describe these cyclical features of the sun as an interaction between the normal magnetic field of the sun and the field that is inspired by the differential rotation of the sun. So you had a regular field. As the sun rotates, it kind of shears and makes a more toroidal magnetic field deep in the sun. And this is a toy model, so a very simplified model, even though the model itself is very complicated. So it doesn't make exact predictions, but broadly, we can expect when the sun will be at maximum or at minimum. And here's that prediction right here. You can see that we've entered solar maximum a little earlier than expected by the model. And that's okay. It's just a model. We're doing the best we can here. We don't know. Stars are complicated. Stars are really complicated. There's quantum mechanics and stuff in there. By the way, side note, is this a grift opportunity? Does the astrology community account for solar cycles, or is that something you and we could get in on? Like, sell solar charts, and if you were born in a maximum, you'll be lucky with your career but unlucky in love, and if you're on a waning maximum, I don't know, it's probably already exists, right? They're probably already doing that. So solar physicists work to study the sun so they can make better predictions on how our sun will behave, but it will also teach them how every single star in our galaxy will behave. So they take lots of daily data on the sun, and I thought it would be fun to go through what's happening to our sun in solar cycle 25, which is what we're in now. So I will link this website below. It's NOAA. There's a nice little video where they do a time lapse of sunspots appearing next to a graph. I'm not going to watch that. But here's some of the stuff happening with our sun. So this is Thanksgiving 2020. Oh man, did you guys see it? Oh man. Okay. Right here in this region. So this is why sunspots are so interesting. They're associated with these huge ejections of mass, So when the sun is active, it means more sunspots, which might look boring in like the red, but it means a lot is going on. Let's do another one. Okay, this is July 3rd, an X-class flare. Let's see. Nice. And these flares are like the radius of the sun. They're huge. They have huge impacts on our whole solar system. That's another good one from October 28th. Oh, this one's a zoom in on that. Pretty good. The version of A Call Your Astro where I walk through a website with you. This one has a handy red arrow. Look at the sun do wild stuff. Okay. Here's another one. Amazing. Okay, so I wanted to read you this quote at the end. The timeless progression of the solar cycle marches on. Although the sun is no more active than in previous generations, our society has changed. With our increasing reliance on electrical power, global telecommunications, satellite navigation, and aviation, we are more sensitive than ever to the sun's changing moods. Stay tuned for more fireworks as we approach yet another solar maximum in 2024. Okay, so let's talk sci-fi. This is why I think this is interesting. Solar maximum is associated with magnetic storms, which can affect communication satellites or, planes flying in the sky. Or if you were in a spaceship, your navigation systems, your physical ship. These storms can be huge and we cannot predict when they will happen. On Earth, they can cause power outages. You can also see effects in literal Earth. Magnetic storms can cause aurora borealis to appear in the south. So where you usually only see northern lights, you'll see a result of a giant solar flare, green aurora borealis in New Mexico. These kinds of things I think would be fun to see in sci-fi. I think it would be interesting to talk about blacking out the sun. One of the things is The Black Cloud by Fred Hoyle. A space cloud just gets in between the earth and the sun. That's a really interesting idea. What if your sun is sick and it's getting sunspots all over it? That's kind of fun. And I'm not saying I never see this kind of stuff in sci-fi. Maybe I should just go watch more Star Trek because that's where you see a lot of it. But I feel like so much of the sci-fi I've been reading and watching recently is just all huge things, boring multiverse stuff, which I'm just not as interested in. But anyway, our sun is also pretty chill, as far as star environments go. We have this really regular periodic moments of maximum solar activity, but most of the time it's pretty chill, and that is not the case for all stars. This is just a brief ad for my Patreon. One of the videos I did on there was about exoplanets. In that video, I talked about the habitability of exoplanets, and I said one of the things when you're looking for a habitable exoplanet is a habitable star, because if your star is too big, too blue, too bright, those types of stars die really quickly. And so even if you had a planet, which you totally could around a big blue star, there wouldn't be enough time on that planet for life to evolve. So that's not a habitable system. And then you have systems like our Earth, where it's a pretty casual, calm, chill star. It's going to live for 10 billion years. There's enough time for the planets to evolve life. But if you move further down to more red stars, like red dwarfs, those stars are just too active to host life. And I just kind of mentioned that in the video and didn't explain it in any way. So that's what I'm going to do now. And you don't have to go watch the Patreon video to understand what I'm about to say. So it's totally fine. I understand that Patreon's expensive. It's totally fine. So what I'm going to do is tell you why you can't really have habitable planets around red dwarfs. And maybe we could try to wiggle a sci-fi way to make it work. What kind of world would that be? In general, in general, I understand there are exceptions here. In general, massive stars are blue. They're relatively stable. They're large in radius. They're very massive. They burn through their material really quickly. They die really young. They might live 100,000 to 1,000,000 years, and they end with a big boom explosion. Okay? In general, on the other end of the spectrum, less massive stars, way less than our sun, are more red. They have smaller radii. They're much more active. We've talked about solar activity, they're much more active. they have smaller radii, and they live forever. The first red dwarfs that were made are probably still alive. They stay on the main sequence longer than the universe has existed. And so you might think that would be great for evolving life. Because I said the problem with blue stars is that they die before evolution can happen. But around a red dwarf, like, you got nothing but time, right? They're gonna live for 17 billion years, 25 billion years. But it's the solar activity that's the problem around a red dwarf. And of course, that was in general. You get exceptions. Space is big, like red giants, for example. They're not on the main sequence, but they're red but big. I'm talking main sequence in general. Okay, so let's set up a habitable planet around a red dwarf star. So one of the things to be habitable, like I said, is the Goldilocks zone. You want to be close enough to your red dwarf star that your planet has heat, but far enough away that it's not on fire. And the thing about red dwarfs is that they're much less massive, so their habitable zones will be much, much closer to the star than when you compare it to like our Earth-Sun system. And that becomes a problem when your major axis of your orbit, that's called A, is really short, when you think about tidal locking. So tidal locking is a process that happens with bodies orbiting each other. So they're exchanging angular momentum until they reach a nice little stable in resonance position. And what tidal locking means for circular orbits is that they will always be facing each other as they rotate around. So for example, the moon is tidally locked to Earth. We only see one side of the moon. That's why there's a dark side of the moon. The moon is always facing us as it orbits around, right? Here's a little simplified equation for the time scale of tidal locking. And you can see at the top it's got a to the 6th, where a is the semi-major axis of your orbit. So the closer you are to the star, the faster you tidally lock. So if we put our habitable planet in the Goldilocks zone around a red dwarf star, it will tidally lock to that star before life can evolve, which means that one side of our habitable planet will be facing the sun at all times and one side will be pointing away, which means one side will be so hot everything will evaporate and one side will be an ice crazy world. That's not really great for evolving life on your planet, so it doesn't really work. Although I have seen some stuff where people talk about like this stripe of land that's like right on the shift between the dark side and the light side, and they can travel to either. That's kind of cool, but I just don't think that works for our purposes. I thought next was like, okay, what if we had a binary planet system, like orbiting, like the moon and the Earth, orbiting around our red dwarf star? You're adding mass to that system, which will lengthen the timescale of tidal locking. And think about it, like the moon is tidally locked to Earth. We only see one side of the moon, but the moon is not tidally locked to the sun. The moon has nights and days just like Earth does. So couldn't that work? And I did a quick back of the hand calculation and it does not. Like the time scale of adding a little mass just doesn't change nearly as much as the a to the 6th in the numerator of this equation. Where you are in the system is way more important than how massive you are. So the little binary thing, what would actually happen, I think, is that the smaller planet would tidally lock to the bigger planet, then the bigger planet would tidally lock to the smaller planet, and then they would both tidally lock to the star, and that would happen, again, an order of magnitude before life would evolve, as long as it was doing it the same way as it does on Earth. So that's out of the question. But then I thought about something else, which is that a lot of the exoplanets we observe are not on circular orbits. And there's a trick to the definition of tidal locking. So when we think tidal locking, like your brain just jumps to the systems in our solar system where most of everything is on circular orbits. So the moon, when we think tidally locked, we think, well, we only see one side of the moon. That's how tidal locking works. But that's not the definition. The definition of tidal locking says that at apogee, which is the furthest point in the orbit, the same face will always be facing the object it's orbiting. And for a circular orbit, like what the moon is on nearly, nothing's ever really circular. For a circular orbit like the moon, we only see that face because it's at apogee every single point in its orbit. But an elliptical orbit, it could work. An elliptical orbit would still have a day that lasts as long as your year. Let me just show you a GIF. So I found someone who made a GIF of this specific situation, and here's their name. So you have one body on an elliptical orbit around another body, and the red arrow is always on the same face of the little guy. And you can watch as it goes around. When it's at apogee, it's always pointing at the same way, but it's still orbiting. So could this work for our sci-fi world around a red dwarf star? Like, you still have rotation, so both sides are getting heat, but you're still in the Goldilocks zone for most of your orbit. Maybe we can make this work. This is still a big jump for habitability, because with an elliptical orbit, you spend most of your time at apogee, which means furthest away from the star. But I mean, you're still rotating, so both sides of your planet are getting direct sunlight. Maybe this could work for our sci-fi world where we're making a habitable planet around a dwarf star. It's made me think of another sci-fi book I've read called A Deepness in the Sky by Werner Vinge. And it's about a star system called On-Off, because the star, for 215 out of 250 years, it's just turned off. It emits no energy. And there's a planet around this star with, aliens, spider aliens. I read it a long time ago. I think it's spider aliens. And, they have to hibernate. It's very interesting. And this is what I'm talking about. I need more of this in my life. Please recommend me books in the comments below. Okay. But the Goldilocks zone is not the only problem with red dwarf stars as habitable stars, because, as we talked about, the solar activity is much higher. So the interesting thing about dwarf stars is that we can measure the dip in brightness due to their solar activity. So just like the sun, they will get sunspots, but they're going to be much larger, and they're going to cause a much deeper dip in luminosity, because they're covering more of the star. The sunspots, like the ones on our sun, they don't last that long. It's like days or weeks. They also are just not big enough to cause that big of a dip in brightness. So even if we were observing a star that was in its solar maximum, the fractional dip in luminosity because of its sunspots would be like in error bars. There was no way we could be able to tell. But with red dwarfs, because the sunspots are so big, they cause like a fractional dip in the luminosity of the star, which is observable. So here's a cartoon that's based on data that looks like this, of what these stars would look like. So imagine our little elliptical planet guy is on an orbit around a star that's just dipping in brightness every few days or every few weeks, depending on where it is in its solar cycle, by like 5%, 10%, 30%. What would happen to the life on that planet? If you were in one of those regions where the eclipse was not totality, and maybe you put on your little glasses and you saw like 30% of the sun covered, you might not have noticed a change in brightness around you. You might not have noticed a change in the temperature. But if we experienced like 10 days of 60% less luminosity from the sun, that would have an effect on things like crops and weather patterns. That would be a huge deal. Imagine how the evolution of a species would change if every 11 years there were periods where the sun was half as bright as it normally was. Like, I imagine your habitable planet would need a source of geothermal energy so that everything was like digging down when it was cold. Like, maybe photosynthesis wouldn't evolve the same way, so plants would be super different. Like, we know solar activity causes things like magnetic storms. Your habitable planet on its nice elliptical orbit would need a huge magnetic field to protect it from all that radiation showers. So maybe that would be the source of geothermal energy. Like, you have some rotating core like we do. And, people could go underground, and maybe instead of plants, like, the magnetic storms cause auroras all over the planet. So you get a bunch of fungus. Isn't that a thing? I'm not a writer. One last problem with these red dwarf stars. Let's just recap the list. So bright, so you have to be closer to the planet, which means you'll probably have to be on an elliptical orbit, which is not great for evolving life, but like, we can make it work. We can fix her. huge magnetic storms, so your planet would need a big field to protect you from like the radiation just pelting you all the time. Evolution would change because you would have these darker periods. Like, what kind of plant life would there be? What would the society be like? Like, would the rich people live underground and the poor people have to be in the dark? Oh, that reminds me of, that's like the time machine, right? With H.G. Wells, where like humans break in evolution to like little babies and monkey people. So that's already been written. The last thing to remember about these M-dwarf stars is not only that you get these sunspots, but you also get these huge flares. Here's a paper of a flare observed in the 90s from that same star. It was this huge burst, just a huge explosion, and we don't really know how these happen. From the star, it kind of goes back to normal. Like, what does that mean for your planet? Like, that would decimate your planet. Unless, you create your worlds where those happen at regular intervals and only when your planet's at apogee far away. So, like, you see it, but maybe it doesn't destroy you. I don't know. But anyway, that's why astronomers say there probably aren't habitable planets around dwarf stars, but people are always coming up with ways to make that happen. But I would love to see that in sci-fi, so let me know if you have any. If anybody is writing a sci-fi novel at this moment and you use any of these ideas, I want to be thanked in the acknowledgements. You don't really have to. It's fine. Send me a copy though. Thank you. If we look at the spectra of the sun, we see something called Zeeman. I've had so many classes and I've heard it pronounced both ways. Zeeman. I think it's Zeeman splitting. That's what I'm going to go with. Zeeman splitting.